All right, I guess you could call this notes if you want. I would recommend, there's two ways to sort of deal with this. If you're one of those people that likes perfect sort of notes and you want to do it in loose leaf and make it all look all nice, then you can go ahead and do that and then cut these out and paste them in after. Probably not the recommended method. The recommended method would be, I'm just going to be talking about them. I've got exactly what you've got up here, and I'm just going to be scribbling notes kind of on the side, and I would suggest you kind of do the same on here. There's generally, I've found over the years, there's enough space on here. Okay, does that work for you? Seems like everyone's in agreement. Okay. So, again, page 38 here, 2.1, analysis of VT time graphs, velocity time graphs. In the last chapter, we found velocities from displacement time graphs by taking slopes at given times. In fact, that was grade 11 for you. In this chapter, we will use these values to create velocity time graphs and analyze them using the three primary analysis methods for graphs learned in the last chapter. So first of all, let's look at constant velocity graphs. A motorcyclist traveling along a straight level road past markers at 40 meters, 100 meters, and 160 meters at the times you read on the graph in figure 2.1a, which is this one right here, right? This DT graph is a straight line. Slopes at 3 points in the graph are recorded in the table in figure 2.1b, right here. Right, so they got found the slope here is 20, the slope here is 20, the slope here is 20. Why are they all the same? Because it's constant velocity, right? Therefore, the velocity is all the same. No big surprise. And then plotted in the graph in figure 2.1c. That's the one right here with the motorbike. And you'll notice that it's flat. Again, no big surprise. The horizontal line of the VT graph shows that the velocity of the motorcyclist remained constant as time passed. Using the read, slope, and area techniques of the graph analysis to discover what information can be gleaned from a VT graph. So underneath there, reading the graph. In figure 2.2, the units on the y-axis are meters per second, which indicates velocity. Since you are reading a given velocity at a given time, reading this graph allows you to find instantaneous velocities. So you can find, right? And you're going to have to decide what you want to write down too, right? You can find v-inst from that graph by just reading, right? It's a graph of velocity. So you just pick your point and you read it, right? And again, they're all going to be exactly the same, right? Because it's constant velocity. Pretty simple to start off. Finding the slope of the graph. To find the slope of the graph in figure 2.2, note that the horizontal graph has no rise. Thus, for any value of delta t, the value of delta v will be 0, and the value of the slope will be 0. Right? So I'm talking here. M is equal to 0. Therefore, do you guys know 3 dots in a triangle means therefore? You do now? Acceleration is equal to 0 meters per second squared. It's flat.
M means slope.
M means slope, correct, sir. Okay? So far, pretty much stuff you already know. The slope calculation produces a value of 0 with units of meters per second squared. This quantity is the change in velocity over a given time period. We can see that if an object has constant velocity, its acceleration must be 0, of course. The process of change in velocity is called acceleration. The units for acceleration are distance over time squared. By finding the slope of the VT graph, we produce the following equation that you used extensively last year. A equals delta V over delta T. And in the very near future, we're going to be taking that and we're going to be expanding on that formula to give you something that's maybe a little bit more useful. Calculating the slope from 2 points in the VT graph gives us the average acceleration. The slope of the tangent on the VT graph gives us the instantaneous acceleration. But when it's constant like this, the tangent line is just straight across, right? A lot of this stuff is really, remember that 2-column thing that we went through last week? A lot of this is the same concepts, just sort of in a different format, right? Finding the area under the graph. Consider positive to be north. In figure 2.3a, the area under the graph forms a rectangle, so its area is obtained by the relationship length times width. In our case, the length is time and the width is velocity, right? Time multiplied by velocity. We can represent the area of the VT graph as V times T, and by doing a unit analysis, we see that meters per second times seconds, and the seconds cancel and give you meters. And you may have done that type of thing. I know Mr. Friesen was big on that, so I'm still referring to this graph up here, you guys, right? So when I go velocity multiplied by time, I'm talking about meters per second times seconds, and the seconds cancel, giving you meters, which means that the area is measured in meters. Area is measured in meters, which goes to our understanding of the area being the distance. And you may remember from way back in probably grade 10, I guess, what is V times T equal to? D, right? Okay, so it all sort of fits together like a big jigsaw puzzle. Indicating that the area represents distance. In other words, the area represents the displacement of the object during the chosen time interval. So area is V times delta T, 20 meters per second times 5 seconds, 100 meters. The displacement is in the positive direction because the area is positive. It's above, right? It's above the zero. I know when I do this with my finger you can't see, but I don't know why I still do it. The displacement is in the positive direction because the area is positive. If the velocity is negative, is in 2.3 b, which you do not have, but it's in the book, then the displacement is also negative. So the results of this analysis are summarized in figure 2.4. So do you have a flow chart at the bottom of your page? I think you do, right? So I would like you to take a moment. Oh yeah, they are here, sorry. So this one is positive, right? Positive displacement. And this one is negative displacement, right? Okay. I would like you to take a moment while I do my attendance. I'd like you to complete this flow chart right here. I know you've got it in the book. It's just basically a copy exercise, but it's sort of so you can see what's going on, and then I'll be right back to join you. All right, so hopefully that didn't take you too long. So when you read a VT graph, you are reading in meters per second, and what are you finding? V-inst, right? Instantaneous velocity. And when you're finding the slope, you are reading it in meters per second squared, which is the acceleration. And when you read the VT graph, the area, you're reading it in meters, which of course is the displacement. So again, basically the same kind of information that was in that little chart the other day, just sort of in a different format, hopefully that is useful to some people. Okay, here's where now we start to, I know I've been saying that for a little while, but it's starting to ramp up a little bit. Graphs with changing velocity. On a performance test, a Honda Civic produced a DT graph in figure 2.58, this one right here. What I'm going to do. As you saw in chapter 1, a curved DT graph means the velocity is changing. Finding the slope of this graph at 4 different times gives the velocities as shown in 2.5b. Plotting these points gives the VT graph in 2.5c. So what did they do? They found slope at the following points. They found slope here, 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 and there by drawing tangent lines. Can you see the tangent lines in there? Yeah. Okay, so they found slope, and they got the values of, I'm just going to make this a wee bit bigger here for you. They found slopes of 0, 6, 12, and 18, indicating that the speed is increasing. Then they took these values here and they plotted them here. And remember, this is a velocity time graph. And once again, you can see that the velocity is increasing. Is it increasing at a constant rate? Yes, it's a straight line. Figure 2.5c shows a steadily increasing velocity. If the velocity increases, the object is accelerated. To find the acceleration, we find the slope of the VT graph, and that is what they do right below that, right? So acceleration is the slope. They've got 18 minus 6 all over 4.5 minus 1.5. Okay? And they just pick those points. Does it matter which points you pick? It shouldn't. In this case here, all the points are exactly on the line, so it really doesn't matter. And so what do they get for a slope? 4. 4 meters per second squared. So in other words, the velocity is changing by 4 meters per second every second, right? 4 meters per second every second. Now they say 4 meters per second squared east. Why do they say east? Position is positive. And because we're talking about a Honda Civic here, it's sort of moving forward. We've sort of assumed that it's going to be east, right? Generally, in our world, things tend to move from left to right. It's just the way we live. And it talks about that in the next paragraph. Finding the area under the graph. The area under the graph in figure 2.6 is a triangle. area under this graph here, right, is a triangle. The area of the triangle is 1/2 the base times the height. By substituting values and units in the graph into the equation, we obtain 1/2 the velocity times time, and thus they get, and I don't really have room for that, do I? I'm going to have to squeeze. Do you guys have room? 1/2 the base times the height. 1/2 the base from 0 to, now should we go to 5 or should we go, what do you think? We should probably go to that first data point, right? Are we going to get the same result? I guess it really depends on what they want to know, right? They want to know, they're using 3.5 in this case here, 2.6. I should give you this graph here, shouldn't I? I must have missed that one when I made the sheet up. So they actually want to only go to 3.5. I'm not sure where they came up with that value, but so they want that right there. So 1/2 the base is 1/2 times 3.5, and the height there is 15, giving us a displacement of 24.5. Right? And if you look over here, let's say 14. Where did I get 15 from? Oh, I see. I just sort of read that off there, right? They didn't do a very good job of asking a question, did they? They made it a little confusing for us. See, this is why I stopped using the book, because it's not written very well. Oh, and then they do this silly thing, round it off to the correct number of significant digits. The answer is 24 meters. Should we have that rant about the significant digits right now? So, top of page 41, example 1, working with negative motion. Repeating the test drive in 2.5 in a westward direction produced the VT graph in figure 2.7. This one right here. Calculate the acceleration and reconstruct the DT graph. So now they're actually asking us a question. They want us to take this velocity time graph and reconstruct, work backwards, so to speak, to come up with a DT graph. Have we done this before? Not really. Okay, this is new. So, finding acceleration. In the standard reference frame, westward is negative, hence the velocities are negative, down below, negative. But that does not change the process of finding slope. In figure 2.7, the slope of the VT graph gives an acceleration of -4 meters per second squared, or 4 meters per second squared west. Although the acceleration turns out to be negative, it's in the same direction as velocity, therefore the object is speeding up. Does that make sense? It's moving west, the acceleration is west, it's speeding up. Okay? So they get a slope here of -4. How come? -8 over 2, right? -4. Pardon me? Maybe they liked my rant, and it just took them a while to understand it. You guys didn't clap for me. Oh, good answer, Joey. Finding displacement. To find displacement, we once again find the area. This time the area is under the time axis and stretches down to the velocity line. Three areas are shown in figure 2.8a. Figure 2.8b is a table of displacements represented by the areas under the velocity graph. These points are then plotted in 2.8c and joined with a smooth curve. 2.8c is a DT graph constructed from a VT graph. Okay, what the heck did they just say? No idea, right? Let me show you. What they did was they have taken these three, do you see these triangles over here that are labeled A, B, and C? Okay, now technically A is this one in black. Technically B is all the way from there in blue. And technically C is all the way to there. Does that make sense to you? Okay, so they found the area of triangle A, 1/2 times 1.5 seconds times -6, and they got an area of -4.5 meters. Does that make sense? And then they found the area of B in blue. They just did the black one, right? And then now B is going to be all of that one. So it's all the way over to 7, right? Sorry, that's not a 7, that's a 3. 1/2 the base time is 3, and then all the way down to minus 12, giving us an area of minus 18. And then they did the same thing for the red triangle. And the base of that one is 4.5. 1/2 the base as minus 18 is 40.5. So now these are the displacements for those 3 points, and then they plotted them on a graph and then did what? Drew a curve. So this A right here is at point minus 4.5, which was the area of the black triangle. And A plus B here is at minus 18. And A plus B plus C, I guess, is at minus 40.5. And then are you surprised that DT graph is a curved line? Why not? Because it's accelerating, exactly. Is the slope increasing in a negative sort of way? It's getting steeper, right? In a negative sort of way, so it is in fact speeding up. Could you take, now if I give you a VT graph, could you come up with the DT graph? Could you work backwards? I think so. You find the area and you work backwards. Okay. Bit of a challenge, but I think it's doable. Let's look at example number 2. When velocity and acceleration have different signs. Immediately you should recognize that this means what is happening to this object. When velocity and acceleration have different signs. What does that mean? Do you know? Let me go back one then, just to confirm. Let me go back to here, and I'm just going to extend this page so I got a little more room to work with. This one is moving negative, right? If the velocity is negative and the acceleration is negative, then this object is no, going backwards and speeding up, right? Remember, it's getting steeper here, Joy, right? Going backwards and speeding up. If the acceleration is negative and the velocity is negative, pardon me? No. As long as it's to the left, then it's negative. It's when the signs are the same that it's speeding up. When the signs are the same, either both negative or both positive, it's speeding up. But in the next one here, example 2, the velocity and acceleration have different signs. So when, say for example, the velocity is this way, but the acceleration is this way, then that means that it's slowing down. Or vice versa. The velocity is to the right and acceleration is to the left. It's slowing down. So, it just says, for the slowing down portion of the roller coaster ride. What roller coaster are they talking about here? Stupid textbook. Who writes these textbooks? Yes. For the slowing down portion of the roller coaster ride, find the acceleration. So for this case, we're going to use the DT graph in figure 2.10, this one right here. So this is a position time graph. We are going to create the velocity time graph, apparently this time. Figure 210 shows the process of creating the VT graph from slopes in the DT graph. To find the acceleration, take the slope of the VT graph. So they took various tangent lines, there, and there, and there, found the slopes to be 30, 12, and 0. Right? Steep, not so steep, 0. And then they graphed 30, 12, and 0. Right? And the velocity is approaching 0 because it's slowing down. Remember that little phrase. Approaching 0 means slowing down. When the velocity approaches 0, it slows down. So that's all they've done here. Right? In this case, the acceleration sign is negative, yet the velocities are all positive. This means that the object is slowing down. The flow chart in figure 211, which you guys don't have, I believe, right? Or do you? No, you don't. Shows how to determine from your calculation whether an object is slowing up or speeding up. I don't think we need it. If the signs are opposite, it's slowing down. If the signs are the same, it's speeding up. You want to jot that down somewhere? I've got it here, right? Signs are opposite, slowing down. Same direction, speeding up. If you want to jot that down in your own words somewhere, that's good. Randy has a question.
Like, in picture 210, like, this is the position time graph.
Yeah?
Where, like, how do you decide which parts do you calculate?
Like where to find the slopes? It makes no difference.
It doesn't.
No. If I no. if I used this point right here, I would have gotten a slope somewhere between 30 and 12. In fact, it would have been right about there on the line, wouldn't it? Right? Yeah. Any points. Yeah, it doesn't matter. How many do you need? I think 3 would be the minimum, wouldn't you say? Like, I guess you could get away with 2, but yeah. Good question. Okay, example number 3. A lot of traveling and ending up nowhere. It kind of sums up today's lesson a little bit in some sense. You will notice in the textbook that the person is riding a bike up a very light green hill. Can you see it in the background there?
No.
In the textbook, not on your sheet. Yeah? Okay, so it probably didn't appear on your, right? If you want to draw it in there, you can. I'm not convinced that it helps. It kind of makes it confusing in my mind. But anyways, so figure 212A is a VT graph of a cyclist motion. The cyclist traveling at 20 meters per second arrives at the bottom of the hill, climbs up the hill to a stop, and then coasts back down again. The total displacement as well as the acceleration, find the total displacement as well as the acceleration for each section. Now, do you have some student's handwriting in that paragraph in your textbook?
Yes.
You should. If you don't, please add it in where it says find the total displacement. Change that to find the total vertical displacement. Okay, because it took me 2 or 3 times through this before I finally figured out what the textbook people wanted me to say. Why is that important here? Because we're talking about the total vertical displacement. How much do they go up and how much do they come down? You can see that this is a very weird hill. It's pretty steep. I don't think you'd be riding your bike up it. You'd probably fall off, first of all, right? So what is the, you can tell by the graph. Oh, I shouldn't have done that. You can tell by the graph what's the total vertical displacement. They went up a hill and they came back down on the other side, and it's 0. You can tell that, right? Hills aren't like that, right? And generally people think about displacement as how far sideways you travel. So it's very confusing. Poor choice, in some senses. Okay, so first displacement. First, calculate the areas of sections of A and B, making sure to keep track of signs. Add the 2 parts to find the total displacement. Consider up the hill to be positive direction. So if you were to find the area here, 1/2 the base times the height. I think this thing needs calibrating here. The base is from 0 to 4, and the height is 20. So 1/2 of 4 is 2 times 20 is 40. In other words, they went up 40 meters. Now, again, back to my little rant about the hill. Is this distance from there to there 40 meters? No. They're talking about straight up and down. How much higher in the air are you than before? Can you read that from the graph? Like, basically, by putting that hill in there, it's kind of implying that it's a position time graph. And it's not. It's a velocity time graph. I don't think the hill should be in there. On the negative side down here, what's the area? 1/2 the base times the height. 1/2 the base is, it's from 4 to 8 seconds. So the base again is 4, and the height is minus 20. So they came down the hill minus 40 meters. Total displacement, 40 minus 40, or 0. I.e., a lot of biking, not getting anywhere. So yeah, I don't think it's the best example. Because the displacement is 0. I don't think hills are generally like that. I don't like the bike in the background. I don't like any much of it. What do you guys think? We're just going to go along with me because that's probably what. Sounds good. Okay. The flow chart, however, is important. I'm unfortunate. Can I drag this down? Yes, I can. Let's do this. The flow chart is important, though. Okay. This basically tells you everything down that right-hand column of that previous sheet in a flow chart form. Okay? Oh, there's actually more to this, isn't there? On the next page. Let's go to the next page, page 44. Acceleration. To calculate the acceleration. Oh, this actually is important. That's right. To calculate the acceleration, take the slope of the line as shown in figure 2.13. Both the negative and positive sections have the same acceleration. This is weird. What's the slope? It's constant. It's a constant what? They found the slope to be? I'm on page 44 now, Paige. They have the slope to be a constant -5. How can this thing be, this bike, how can it be going up the hill and slowing down, and then going down the hill and speeding up, but yet the acceleration is constant? Well, it is. Can going, and it is. Okay? Here's the deal. It's going up the hill and it's slowing down at it, he or she or whichever gender it is, can't tell. It's slowing down at a -5, but because then it's going down the hill, it's speeding up at the same rate. Assuming, of course, that the incline of the hill up is exactly the same as the incline of the hill going down. The hill is like a giant cartoon peak like this. A better analogy would be, let me just write it here. A better analogy would be this. What's gravity here on Earth? The number? 9.8, right? If I throw the ball up, on the way up, the ball does what? On the way up, what's happening to the velocity? Slowing down, right? As long as I don't hit the roof. It's slowing down. On the way down, it's speeding up. How fast is it speeding up on the way down? -9.8. How fast is it slowing down on the way up? -9.8. Going up, which way is the velocity vector? Up or positive? Which way is the acceleration vector? Down or negative? The signs are opposite. I kind of feel like John Travolta here. Signs are opposite, so it's slowing down, but when the velocity is down and the acceleration is down, the signs are both in the same direction and the ball is speeding up. Is that the same thing that's happening here? Yeah, the cyclist is going up the hill. Which way is the velocity vector? Up. Which way is the acceleration vector? Down. John Travolta. Object is, cyclist is slowing down. Coming down the hill. Which way is the velocity? Down. Which way is the acceleration? Down. Both down. Object is speeding up. Can they be the same constant velocity, same constant acceleration? Yes, I've shown you that here with the tennis ball. The Earth doesn't know that your tennis ball is going up in there. Oh, well, I'll change gravity for this particular second or so. I'll change it to, I don't know, maybe -7 or +7 or whatever, right? It's -9.8. It's always on and it never comes off. Up, down, sideways, acceleration is always down at -9.8. Constant. The difference here is that hills aren't generally like that, right? This hill would not look like this. You wouldn't have constant acceleration if the hill was like that. The only way for this thing to be true would be if the hill looked like what? The hill would have to be a perfect peak like that. The line would have to be straight on the left-hand side, like the slope, and the slope would have to be perfect down on the right-hand side. And I'm not really sure what would happen here at the peak. Good luck riding your bike like that and then immediately turning back down and going down the hill. Completely made-up situation. Let's go right to here. Let's just skip right to there. This is the important part. Okay, so when you've got a VT graph, what do you read off the VT graph? Yes, V ints. When you're looking at the slope of the VT graph, you are looking at the acceleration. If you use 2 points, then that means you're finding average acceleration. Can I abbreviate with A bar? And if you're using 1 point, then that's because you are using a tangent line, which you still have to use 2 points to actually find the slope, but you're finding the slope at a single point. And then we're talking about the instantaneous acceleration. When my tennis ball is going up in the air, just after it leaves my hand, like about here, somewhere right about there, what's the instantaneous acceleration? After it leaves my hand. Is it not minus 9.8? Minus 9.8, minus 9.8, minus 9.8, minus 9.8. What about when it's right at the peak, just as it stops and comes back down? Is it minus 9.8? Does gravity turn off for an instant when tennis balls reach the peak of their trajectory? No. Gravity is always on, minus 9.8. So even though the ball isn't moving for that instant, acceleration is still minus 9.8. When you're looking at a VT graph and you're finding area, you are looking at displacement. And when you take area divided by time, well, then you're looking at average velocity. I've given you a lot to think about, haven't I? It's going to take a while to sink in. It's going to take some questions to sort of work through all this stuff. What do you say?
What?
I don't know. Are you ready to try some stuff? On page 46, there are 4 questions. 1, 2, 3, and 4. I'm going to give you the rest of this period. You've got 25 minutes to work on those. There are some on page 69 as well. Oh yes, and being the smart man that I am, instead of, if you flip to page 69, you'll see these graphs here, but of course people want to mark up the graphs, they want to be able to use them, and so what I did was I photocopied the graphs out of the book that you have, and you've got them on the sheet here. So that's your own personal copy, you can make marks on it, you can do whatever you want. Okay, so here's the plan. I would like you to do questions 1 to 4 on page 46. Let's plan to correct those tomorrow. Okay, I'll give you a little bit more time to work on page 69 graphs. And of course, I always provide solutions, and I think they're here. They haven't come out yet, they're on the shelf. Here they are. Okay, the white binder. Yeah. Grade 11 is red, you guys are white. No! How am I supposed to remember that? Put the red one says 30x. Where would you like the white binder to live? Side, back. At your house. For now, I'll put it over here. We'll see where it ends up. It tends to end up just sort of floating around, okay? But all the solutions are in here, and as far as I know, all the solutions, everything here is on Schoology link. If it's not, let me know. I'll have to relink, but all the solutions are available. Do not ever say, I can't get the solutions. I have them all, I just may not have linked them to you. But they're always here in the white binder, okay? Good luck.